Hello and welcome to another class of ATMO 620. I hope that you're all doing well. I hope that you've enjoyed the semester so far and the class so far. Today we will continue talking about radiation. And in particular, we will talk about a very important topic that is greenhouse effect. As you might have heard, this is sort of a controversial topic for some weird reason, but we will see today what are the causes of the greenhouse gas of the greenhouse effect, and how we can compute certain things really easy to show the basis of the greenhouse gas. You may or may not want to use this with your uncle at like Thanksgiving dinner or Christmas day meal to convince them that climate change is real. But anyway, without further ado, let's start with a little bit of a historical tour of the greenhouse effect. So one of the things that many people don't realize about the greenhouse effect is that it's not something that has been discovered recently using our climate models and such, but it's actually something that's been discovered, that's been known for a very, very long time. And the roots of the greenhouse effect go all the way back to the mid-19th century, so the Industrial Revolution time. And one of the first people to suspect that there may be something like the greenhouse effect was this chap that you see on the slide called Fourier. So this is the French mathematician / natural philosopher who introduced the Fourier transform, the Fourier series, and the Fourier theory of heat. So his name is associated to many, many things. But one of the things that he's not particularly known for is the fact that he started to understand that that maybe gases in the atmosphere could affect the thermal balance of the Earth. In particular, he was one of the first ones to speculate that that greenhouse gases were important to keep the Earth warm and warmer than it would be without them. I don't know if you remember at the very beginning of the class, and probably we'll talk about this. We will talk about this a little bit more later on today. But at the beginning of the class, we discussed how without the atmosphere, the average temperature of the planet would be something like 255 Kelvin, which is way, way colder than it actually is, okay? And so Fourier was one of the first ones to say, yeah, well, actually, you know what? It could be that these gases are playing some role, and that this is important for the atmosphere. Now, the first person who showed that we know of that certain gases can affect the propagation of infrared radiation, certain gases can absorb and emit in the infrared, was John Tyndall. And Tyndall realized that and proved that CO2 and NH4 can indeed have a role in the infrared spectrum. And it was only later, a few years later, at the turn of the century, that Svante Arrhenius, a Swedish scientist, a Swedish chemist, realized and computed actually the effects of CO2, changes of CO2 in the atmosphere. Okay, he was interested essentially in how decreases in CO2 concentration could lead to ice ages, and he computed. He made some calculations, and he also speculated on the role that the gases emitted by the Industrial Revolution could play in in the balance of sort of the radiative balance and the to regulate the temperature of the atmosphere. Bizarrely, his estimate was actually quite accurate, and the only reason why his estimate failed was that he had predicted an increase in CO2 emission, which was considerably lower than what it actually is. So he was, he was even a bit too optimistic a person in that. But this is just to show that the theory of greenhouse effect, of the greenhouse effect, has really, really deep roots that go further back in time than just computer models. A bit closer to us, there was a scientist called Charles Keeling who took measurements of atmospheric CO2 at the South Pole and also at Mauna Loa since the 50s. And the curve that of these measurements, accumulated through the years, became known as the Keeling curve, which you might have heard. And it demonstrated, this is the Keeling curve here, it demonstrated how every year there was a constant increase in greenhouse gases, and particularly in CO2 concentration that had been emitted in the atmosphere. And they showed that, combining these measurements with measurements in Antarctica, in the ice cores in Antarctica, these measurements showed that while levels had been pretty constant for, the past 1,000 years, more or less, at about 280 ppm, we were on a continuously growing curve of CO2 concentration. And right now, we are at about 410 ppm, which is, not twice as much, but yeah, it's considerably higher than what it has been in the past 1,000 years. And then there have been, numerous contributions in the 60s of people like Manabe and Weatherald and Jim Hansen, who started realizing that something bad was really, was happening. And this is pretty much how the modern theory of climate change, if you will, kind of got to be. And so let's go back to that picture that we had at the beginning of the class, where we had the sun that was radiating as a black body with a certain radiance, or what we call a solar constant. And let's assume that the beams come parallel to the Earth. The sun obviously would be emitting rays everywhere, but it's so far that we can say that this is just one sunbeam, one giant sunbeam. The cross section of the Earth would be 4 pi radius of the Earth square. Okay. I spent all the class saying, the cross section is not the surface. The cross section would be pi r squared. Pardon me. And therefore, the power that is absorbed on Earth is Fs, the solar constant, times this, times what is actually retained, and this is called the albedo, which we assume to be 0.3. What is radiated out is 4 pi r squared times sigma t to the 4. At equilibrium, these two have to be equal, and this is how we computed that the effective temperature of the Earth was 255 Kelvin, which is really low. It's about 10 degrees. What am I saying? It's about 20 degrees below zero, to 20 Celsius degrees below zero, which is definitely not okay. And so that's when we said we need to use something a bit more clever, and we sort of postponed the discussion until when we would have the tools to understand and to discuss that. Okay, well, now we have those tools, and let's try to actually check that this is what's going on. Our simple model will be changed in the following way. Instead of having So before we had radiation that was coming in with irradiance F0, and we had a flux that was emitted from the Earth Fg. Okay. Now we will modify this by including an atmosphere. Okay. And the atmosphere has two properties. First, the atmosphere can radiate, itself, and so we'll assume that the irradiance of the atmosphere is called Fa. But also, the atmosphere can transmit and absorb some of the gases. Okay, and so we will call TSW the transmittance of the atmosphere in the short wave, TLW the transmittance in the long wave. Okay. And so it makes sense that something is coming in. Let's assume that the atmosphere is all at the same temperature. It's an isothermal atmosphere, okay, just to simplify things a little. Okay, so we have a solar irradiance coming in, F0. Something is transmitted, and so what comes through and reaches the ground is TSW F0. This will then be re-emitted as Fg with the radiance of G, and some of this will be transmitted outward to space with TLW Fg. Okay, transmittance is by definition the fraction of the radiation that is transmitted to what is coming in. Okay, and plus there are these two irradiances. Okay, if we are at equilibrium, much like before, the equilibrium condition was to say that, we can write it here, before we just said F0 is equal to Fg, okay? And also, to simplify things, let's assume that F0 is we're already taking care of albedo and such, okay? So before we were just saying F0 equals Fg, and at equilibrium, these two had to be the same, and that gave us a temperature. Now at equilibrium, we have to assume that what is coming in equals what is going out, but now we have two spaces, one which is outer space and one which is close to the surface. And the balancing conditions now are that what is coming in is F0. This equals what is going out at this level, and that is Fa plus TLW Fg, okay, close to the surface. The condition will be that what is going out, which is Fg, equals what is coming in. So this is Fa plus TSW Fg. Before we had one condition, now we have two conditions. What do we do with these two conditions? Well, if you take, now I'm pretty sure I have it on the other slide, but if you subtract these two, you would have that F0 minus Fg equals TLW minus TSW Fg. Okay. Let's move on here. Okay. And therefore, we are looking for, yes, we are looking for Fg, right? And so, yeah, you subtract these two. Oh, sorry. Oops. Sorry. My bad. My apologies. I'm just realizing now. Yeah, that's something was not something that did not look good. And so this is TLW Fg minus TSW F0. Now let's collect all the Fg on one side and all the F0 on the other side. This will be F0 times 1 plus TSW equals FG times 1 plus LW, TLW, sorry, which means that FG equals F0 times 1 plus TSW divided by 1 plus TFW. Easy peasy, right? Similar to the condition we had before, but we have this new rational function that complicates things. Why is this useful for us? Well, because we are assuming Stefan-Boltzmann's law, according to which Fg is sigma Tg to the fourth power. And so now, much like we did before, and before we were taking, before we had the T was F0 divided by sigma to the 1 over 4, right? Now it's kind of the same, but we have this term now. This term, if TSW equals TLW, meaning if the atmosphere is just as effective as at transmitting or absorbing, it's just as transparent to shortwave radiation as it is to long-wave radiation, then nothing changes. But if the atmosphere is actually not the same, but has different behaviors in the shortwave and the long wave, then things are a bit different. Okay. In particular, our atmosphere has relatively weak transmittance in the long wave, meaning that it absorbs long wave radiation a lot. Okay, and it has pretty large shortwave transmittance, meaning that it's quite transparent to shortwave radiation. So what does this mean? Is that this number will be small and this number will be large, right? And so this will, in principle, be, if TSW is larger than TSW, then all this is bigger than 1, meaning that this will be bigger than F0. And so, thanks to the transmittance in the long wave being higher than the transmittance in the short wave, we actually have a warmer planet. And if you plug in these numbers, 0.2 for the transmittance to the long wave and 0.9 for the transmittance in the short wave, you get an effective temperature for the Earth of 286 Kelvin, which is really, really close to 288, which is what we have on Earth. Okay. Obviously, these values were kind of chosen so that we would have. But you can see what the point was. You can see why we did that. And you can see really the essence of the greenhouse gas. Like, this is all you need to know about the greenhouse effect. It's not so much that we have gases in the atmosphere, but the fact that we have gases that are opaque in one part of the spectrum and transparent in the other part of the spectrum. If you had if you had the opposite situation where transmittance is large in the long wave, meaning that you're transparent in the long wave radiation, but small in the short wave, meaning that you're opaque, that would be an Earth that is completely sort of, I don't know what's a good equivalent, but it's, just sort of covered by some really dark cloud that essentially doesn't let any radiation come in. It's pretty happy to let the radiation go out, but it's not happy to let it come in. And in that case, this number would be much smaller than 1. And as you'd expect, the temperature would be even lower. Okay? Okay. You can also do, remember that we had 2 equations here, right? Once you know Fg, you can also do the calculation for Fa, and this is what the irradiance of the atmosphere is. Something similar to Stefan-Boltzmann's law holds for the atmosphere, and you can compute the temperature of the atmosphere in this simple model. and that would be 245 Kelvin, which is kind of an average, of tropospheric temperatures. Near the tropopause, you have minus 60 Celsius degrees, which is 215 Kelvin. Near the surface, you have 285 Kelvin. And so the average of these is about 250 Kelvin. So that's kind of close. But again, this is really, really kind of a simplified model. Okay, so the results that we derived until now are they're being derived in sort of a simple settings, right, where you had a single layer of atmosphere in isothermal equilibrium. Well, things are a little bit more complicated, as it turns out, and now we will consider two more complicated cases. The first one is a case where we have an optically thin stratosphere on top of the troposphere. Another one where we have an homogeneous atmosphere where temperature is varying in height. Okay, these are still very idealized models, much like the spherical cow I showed here, and we'll see how to make them a bit better at the end of this class. Okay, so how do we introduce the stratosphere? Well, very simple. We just put this layer on top here, and we assume that the stratosphere is optically thin, meaning that it lets things go through with no problem. So solar radiance F0, it goes through and it remains F0. Stratosphere will radiate F strat in both directions. But then the radiation that is coming from the troposphere, the long wave radiation, some of this will be absorbed. The fraction that is absorbed is epsilon. And what is let through is 1 minus epsilon F troposphere. And T long wave from the ground will have a similar fate. Okay, so equations now are more complicated because you have to take into account the effect of the stratosphere. And in particular, what the stratosphere emits towards the ground will also, some of it will be retained by the troposphere, and some of it will make it finally to the ground. But yeah, so the equations now become a little bit more complicated. As before, the irradiance of the stratosphere is given by Stefan Boltzmann law, assuming that the stratosphere is a great body with efficiency epsilon. Okay, and I will not bore you with the calculations, which I leave to you. But essentially the trick is the same as before. You have to balance all the irradiances and write the three equations: one for kind of outgoing stuff, outer space, if you will; one for the tropopause, this region here; and one for the region near the ground. What is going up has to balance what is coming down, and they have to balance exactly. Okay. The interesting result that we find at the end of the day is that, first of all, we can compute the temperature of the stratosphere, and the temperature of the stratosphere is, again, you can compute it with Stefan Boltzmann law and with these balancing equations, and it's about, in this simple model, it's about 214 Kelvin, which is roughly 60 degrees Celsius below zero, which is not too bad. For the stratosphere. And also just skip to the final slide here, which is really what the point I wanted to make. We finally obtain, from the balancing equations, we finally obtain a formula for the temperature of the ground here, okay? And a formula for the troposphere. Now notice that if we had no if we had had a stratosphere that lets everything go through, okay, so that it's optically thin in the visible short wave and optically thin in the long wave, then that means that epsilon would have been 0, okay? And if epsilon is 0, this goes 0. These 2 over 2 simplify to 1. And, well, lo and behold, unsurprisingly, you end up obtaining exactly the same formula that we had before without the stratosphere. That this should come as no surprise. Yeah, so this allows you to predict temperature of the ground and also temperature of the troposphere, assuming that the very little is absorbed in the long wave, so about 0.1, okay, and using the same values we had before. Now notice that the temperature of the ground is 288 Kelvin, which is exactly what is, you know, on average the ground temperature, and also the tropospheric values change a little bit. So even though the stratosphere is really, really high and doesn't really do much with incoming shortwave radiation, and does relatively little with outgoing long-wave radiation, it still can have a measurable impact even on ground temperatures. Okay, so the stratosphere is cool, but there's still something missing, and in particular, we can do a little more. And the way that we can do more is by assuming that the atmosphere is continuously stratified, meaning that instead of having just one single layer of troposphere, you have a continuous, an infinity of infinitesimally small layers, if you will. Okay, we will assume that the atmosphere is in radiative equilibrium. Okay, radiative equilibrium meaning that essentially the temperature is given by radiation, if you will. It's controlled by how much radiation is interacting with the atmosphere. This tends to be a good approximation, as we saw in the stratosphere, more or less, where absorption and emissions kind of balance each other out. We know it's not a good approximation for the troposphere, but let me just use this simple approximation. We'll use a diffuse approximation, so just remind everyone that the diffuse approximation is that you have sort of plane parallel, two-stream, outgoing, incoming, and you have to consider an effective path, optical path. And finally, we will assume that the atmosphere is gray in the infrared, meaning that the extinction coefficient does not depend on the frequency. Remember this because this is the only time I'll mention this in class, but this is a common approximation often when dealing with climate models. Or when you're doing when you're using approximations in climate models, sometimes people say, oh, let's assume that there is a gray atmosphere. That's what it means. Okay, well, the equations for spectrally integrated long-wave irradiances are given simply by these two. If downward arrow is incoming, this is outgoing radiation. This is Planck's function, which spectrally integrated is simply the function, the Stefan-Boltzmann law that we knew. These are this is known as the two-stream approximation, where you just have outgoing, incoming, two-stream in this sense. There's no interaction, there's no angles and whatnot. And this represents the contribution from the atmosphere, and we'll assume that this contributes equally in both directions, right? Pretty much as we did before. We assumed that the tropospheric layer was emitting upward and downward, and this is a similar idea. Now, for simplicity, we'll assume that the atmosphere is transparent to shortwave radiation. Okay, so TSW is 1. Everything is transmitted. And this also means that the heating rates due to the shortwave are 0. Okay, but if the atmosphere is in radiative equilibrium, this means that long-wave heating also must be 0, which means that net heating is independent. Upward irradiance is independent of height. Okay. Which, I mean, this just follows from this formula here. Okay. And this constant, so this f up minus f down, is a constant. And this, if you assume some kind of a simple boundary condition, you can determine this this constant. Okay. Very good. But then we can start playing a little bit around. And in particular, we sum these two equations here. If you sum them together, you have a difference and a sum, and the Planck's function. So difference, sum, and the Planck function. Okay. But we said that the difference, the net irradiance, was 0. So this vanishes, and it gives you a constraint on the sum of the upward and downward going radiation. You can then do the opposite, and instead of taking the sum of these two, you take the difference between the two, which will give you the difference between the two equations, will give you a 0 here, derivative of the sum plus the difference between the two, which is what I wrote here, okay? And the difference, I took it on the right-hand side. That is a constant that we can determine. And so the sum of these two is a linear function of the effective optical path, okay? Which we can determine again with some kind of constant. Okay, so we have one equation for the sum, another equation for the sum. Well, we can manipulate things a little bit, and we have an equation for upward and downward irradiance. And in addition to that, which is pretty important, you can also derive a function, you can derive what the temperature looks like as a function of the effective optical depth, which is, if you will, as a function of height. Okay, so this gives you a way to determine the temperature of the atmosphere as a function of height, which is really, really nice. Okay, so the equations we derived now apply within the atmosphere. Okay, but then what about the ground? Okay, now if we are assuming that the ground emits as a black body, okay, then the irradiance has to balance the irradiance coming out of the ground has to balance the term above, okay, and the term just above the ground is this term here, okay, and so these two have to balance each other, okay, as to balance each other completely. Now we can even solve these equations very simply. And in particular, we can assume that density decreases exponentially with some height scale HA. And if you do that, then you can find a simple function of the temperature decreasing as a function of height. Okay, this is just a function of what the temperature would look like as a function of the scale height. Okay. And this is just what the upward and downward irradiances would look like. Okay. Now, we call emission height the height at which T equals the effective emitting temperature. Okay. And this, in our example, this happens where chi star equals to 1. Okay. And another important quantity is the so-called skin temperature, which is the temperature that we obtain when we send z to infinity, which is equal to the stratospheric temperature that we had derived earlier, perhaps unsurprisingly. But so, I mean, how can we have this problem? Like, how can it be that there is a discontinuity at the surface? Why is there this inconsistency that, as you approach the temperature, as you approach the ground in the atmosphere, you go to a limit, but the actual temperature of the atmosphere of the ground is different, right? Discontinuities are always a sign that something has gone wrong in the assumptions that we have. That we have adopted. discontinuities are always the sign of something unphysical happening in your model. And in our case, the unphysical thing was to assume radiative equilibrium. If you remember, I think it was last class, we talked about heating rates, and we talked about how heating rates kind of balanced each other in the tropopause and the stratosphere and even above to some degree. But in the troposphere, the troposphere, there was not an equilibrium, and the long wave cooling tendencies were stronger than the short wave heating tendency. And so we said this means that the troposphere is not in equilibrium. And, this is for better or worse. This is why we have weather, right? Because the troposphere is not in equilibrium. And so something else is happening here that solves this discontinuity. Also, one thing I forgot to say that I see now on the slide. If you were to compute dt e dz, right, what we call the lapse rate, how temperature decreases with height, this is much greater than the dry adiabatic lapse rate, which I remind everybody is G over Cp, which is roughly 10 degree Kelvin per kilometer. Okay. Is that correct? Yes, more or less. 9.81 Kelvin per kilometer. Yeah, so the dry lapse rate is the coolest, or the highest degree of cooling, the highest cooling rate that you could possibly encounter in a dry atmosphere. So if you had a rate that was actually greater than that, it means that the atmosphere would be unstable even to dry parcels, meaning that it would be boiling in order for to sort of recover some kind of a stability. And so what happens, and I kind of give it away, but what happens in the atmosphere that makes things, that solves everything, that makes things, that saves the day? Well, what happens is that the atmosphere being a fluid, it can convect, right? You can have motions of fluid that would take parcels from one point to another. And so when you have a situation where you have, your atmosphere is going down, the temperature is going down like this, and then you reach the ground and it becomes really, really hot, what would happen in the real atmosphere is it's exactly the same thing as when you boil pasta, right? You heat up the bottom, and this suddenly, the bottom suddenly becomes much hotter than the rest. And obviously, it's not a discontinuity, right? The bottom would be really hot, and then there'll be sort of some diffusion of heat right above, that would heat up the fluid right above the bottom. And in reality, when you don't have, even without considering phase transitions, you have convection that develops. When you pass a certain threshold, when the fluid at the bottom is warmer than a certain threshold, you start to develop Rayleigh-Bernard type convection, right? Much like when you're starting to heat up some, water or some viscous fluid in a pot, right? Convection is important for a variety of reasons. One of the reasons is that, as you could imagine, it redistributes heat in the atmosphere. But not only that, it also redistributes water vapor in the atmosphere. It redistributes momentum in the atmosphere. Convection mixes and redistributes many things in the real atmosphere, and not accounting for it is a big mistake, right? Or if you will, this is one of the reasons why convection is so important, because it needs to kind of balance out the atmosphere. And so here I wrote, instead of radiative equilibrium, I wrote this new thing called radiative-convective equilibrium, meaning that the new equilibrium would be, we could think of a system as being controlled by two tendencies, if you will. On the one hand, the radiative tendencies that are doing something, and on the other hand, convective tendencies that are redistributing heat, or in some cases, they're also heating up the atmosphere. Why would they be heating up the atmosphere? Well, because when you have convection, and when you have convection that generates clouds, the generation of cloud releases latent heat, and the release of latent heat essentially is then, contributes to heating up the atmosphere. And so if you had purely radiative equilibrium, this is a plot of temperature versus pressure or altitude. This is the behavior of temperature in a purely radiative equilibrium. Okay, notice that up until from 10 kilometers upward, these make very little difference. But with purely radiative equilibrium, you'd have a temperature that would cool down real quickly. And so at 10 kilometers, you'd have something like 180 Kelvin, which is like minus 100 Celsius degrees. This is the dry adiabat, so G over minus G over Cp, okay, which is what we discussed just last slide. Okay, so this is what you'd expect from a parcel, and I think we talked about this in the microphysics part. If you had like a parcel that contained only air, no water vapor, and the parcel goes up, adiabatically, so there's no exchange of heat with the surrounding environment. The parcel will expand, and the expansion will cool it down, and it will cool down according to this profile. If you were to take into account convection, then you get to a new state that is called moist adiabatic. Okay, and moist adiabatic state is this graph here. Notice how much warmer it is than the dry adiabatic lapse rate. Okay, and the moist adiabatic lapse rate is between 6 and 6.5 Kelvin degrees per kilometer. Okay, so it's 4 degrees per kilometer warmer than the dry adiabatic lapse rate, and it's actually a pretty good approximation of the tropical atmosphere, not in Hawaii, but in places like near the equator, for example. Okay, where you don't have where you're not in the sort of subtropical region. Well, then it will be a pretty good approximation. And also notice another important thing. Notice how the tropopause that we could consider as the minimum point of this curve, also notice how it changes quite considerably, like how it goes up from the purely radiative equilibrium to the moist adiabat. It goes from 9 kilometers to about 12, 13 kilometers, which is a lot closer to reality. And so the latent heat release of clouds is actually really important, and it needs to be taken into account as well in order to give profiles that are convincing and close to reality. One thing that we should mention is that, okay, so here we're talking about radiative-convective equilibrium, which is some approximation that one could use for certain areas on the planet, but it's not a perfect approximation. Okay, so sometimes people think of radiative-convective equilibrium as being a good approximation for areas like Western Pacific, where you have really hot sea surface temperatures, and you're close to the equator. When I say Western Pacific, I mean sort of equatorial region of the Western Pacific. You're close to the equator, and so you don't have synoptic variability. You don't have a lot of large-scale forcing that can influence what happens. And so people think of this as a good approximation to radiative-convective equilibrium, but it's somewhat debated whether this is actually a good approximation or not to the real atmosphere. It kind of depends on who you ask. I wrote most of my papers on radiative-convective equilibrium instead of thinking about using radiative-convective equilibrium as a way to conceptualize the real tropical atmosphere. So if you were to ask me, I would say, yeah, I mean, it's actually a pretty good approximation. We could go with it. But if you ask, some observational scientists, they may not be as excited as I am with radiative-convective equilibrium. I remember once I gave a talk, and before giving the talk, I was meeting with the chair of this department. And, he went on and on for like half an hour about how radiative-convective equilibrium was completely unrealistic. And so, imagine how I felt when I started the talk, and I was like, okay, so today I'll talk about radiative-convective equilibrium and how we can think of this as a good way to conceptualize the tropical atmosphere. So I think that, personal stories aside, one needs to be always careful with the assumptions that one makes. And I think that it kind of depends. When you want to use a certain limit or a certain approximation to conceptualize something, to get rid of complications of the real world, you have to be mindful about what you're trying to do and why you're trying to do that. And so if you want to study some clouds, then maybe it's okay to study using real life soundings, or studying radiative-convective equilibrium probably doesn't make much of a difference. But it has been shown that cases in radiative-convective equilibrium can display certain fascinating organization phenomena, spontaneous organization phenomena like convective aggregation. And so then it gets kind of tricky when you say that, this idealized model displays certain features, and therefore these have to be real. So, just be mindful of that. Okay, so this concluded this part on the greenhouse gas. Please feel free to share your slides with your crazy uncle at Thanksgiving dinner. And if you have any questions, please feel free to email me. Otherwise, I will see you for next and last class, actually, on radiative feedback.